Hi everyone. Today we're going to study connectedness and components. When does a computer network have the property that every pair of computers can share information if messages can be sent through one or more intermediate computers? When a graph is used to represent this computer network, where vertices represent the computers and edges represent the communication links, this question becomes: when is there always a path between two vertices in the graph? Let us define some terms. The first is connected vertices. Two vertices U and V of a graph capital G are said to be connected if there exists a path from U to V. Next is connected graph. A graph capital G is said to be connected if every pair of vertices in graph G are connected. Example, we have this graph. The graph is connected because there is a path between every pair of distinct vertices. Next is disconnected graph. A graph which is not connected is said to be disconnected. A disconnected graph is the union of two or more connected subgraphs, each pair of which has no vertex in common. These disjoint connected subgraphs are called the connected components of the graph. Example, we have this graph. The graph is disconnected. For instance, there is no path between vertex A and vertex D. Next term is connected component. A connected component of a graph is a connected subgraph of largest possible size. Note, a graph H is a connected component or component of a graph G if and only if, number one, capital H is a subgraph of capital G. H is connected. No connected subgraph of G has H as a subgraph and contains vertices or edges that are not in H. Example, we have this graph. This is graph H. The graph H is the union of three disjoint connected subgraphs, namely H sub 1, H sub 2, and H sub 3. These three subgraphs are the connected components of H. We have these theorems. Number one, if a graph G has exactly two vertices of odd degree, then there must be a path joining these vertices. Second theorem, a graph G is said to be connected if and only if its vertex set, capital V, can be partitioned into two subsets, V sub 1 and V sub 2, such that there exists an edge in G whose one vertex is in the subset of V sub 1 and the other is in the subset of V sub 2. Next theorem. If graph G is not connected, then complement of G is connected. Next theorem. A graph with n vertices and k components cannot have more than this number of edges. The formula is n minus k multiplied by n minus k plus 1 all over 2. Let's continue to define some terms. Let's define distance. Let U and V be any two vertices of the connected graph capital G. The distance between U and V is denoted by d of UV and is defined as the length of the shortest path. Next term is diameter. The diameter of a connected graph G is denoted by diam of G and is defined as the maximum distance between any two vertices in G. Next term, cut vertex. A cut vertex of a connected graph G is a vertex whose removal increases the number of components. Let's define bridge. A cut edge or bridge of a connected graph G is an edge whose removal increases the number of components. Let's define cut set. The set of all minimum number of edges of G whose removal disconnects a graph G is called a cut set of G. Thus, a cut set capital S of a graph capital G satisfies the following properties. Number 1, capital S is a subset of the edge set capital E of the graph G. Next, removal of edges from a connected graph G disconnects graph G. Next, no proper subset of G satisfies the condition. Note, if V is cut vertex of connected graph G, then G minus V is disconnected. A cut vertex is also called a cut point. Example 1. Find all the cut vertices of the graph. A cut vertex of a connected graph G is a vertex whose removal increases the number of components. In the graph here, there is only one component. Look at vertex C. If we remove vertex C along with the edges connected to it, the graph becomes like this. From one component, it becomes two components. Therefore, cut vertex is this vertex C. Example 2. Find all the cut vertices of the graph here. There are two cut vertices here, whereas removing each would result to two components for the graph. First is the vertex C. If we remove the vertex C along with the edges connected to it, the graph becomes like this. From one component, it becomes two. So, vertex C is a cut vertex. Next is the vertex D. On the same way, if we remove D along with the edges connected to it, the graph becomes like this. From one component, it becomes two. So vertex D is a cut vertex also.